Hello, welcome back to Water Resources. This is the first lecture in the Fluvial Geomorphology module, but I'd like to point out that in a previous module on hydrology, we did have a lecture on Fluvial Geomorphology, and I'd like to point you back to that lecture and suggest that that might be a good review for some of the concepts that are embedded in the module for this week, but things that I'm not necessarily going to go back and rehash since it's easy for you to go back and rewatch that lecture. Where I want to start out today is an overview of streams and what their function is on the landscape and what their purpose is. And this is going to lead us towards a couple of questions. One, what is stream equilibrium? I've called this particular lecture a stream's job, but I could also have called it the Zen of streams. Streams are always seeking some balance between those watershed factors that we've been talking about all semester. Remember, those are important. You should keep looking at them. And a balance with its morphology. So the stream and the size of the channel, the shape of the channel, the type of channel that it is in terms of how it meanders across the landscape and so forth, are all a reflection of an equilibrium with the watershed and those watershed factors. So keep that in mind as we go through this lecture. The other question that we're headed towards is, what shapes a channel? Why is the channel the shape that it is? So let's get started. So let's start with a job description for a stream. Suppose you were running an advertisement and looking for a candidate for a new position to be a stream in your watershed. You might ask yourself, what do streams do? So what I would suggest you do is pause the video right here for a few moments and ponder that question and maybe jot down either mentally or on your notes some ideas about what exactly do streams do in the landscape. All right, so here's some of the things that I came up with as I thought through this question. Well, streams move water, right? We have water on the landscape. Eventually, some of that water drains through the soils down the hill slopes or reemerges out of the groundwater, and the streams move that downstream to another portion of the landscape or to a larger watershed. Also, you may have come up with the idea that streams move sediment. And by moving sediment, they shape the landscape through both erosion and deposition. Importantly, streams maintain and host ecosystems. This function is the one that, in terms of regulations, is probably the most important. Many of our streams that are regulated through the Clean Water Act, the Federal Act, and the complementary laws at the state level are maintained to maintain their function as ecosystems and to maintain the ecosystems that they provide. And a big part of what we're doing in trying to protect streams is to protect those ecosystem functions. And then also, as we talked about way back early in the semester, the hyporheic zone. Streams are the connection between the groundwater or the aquifer and the surface water. And there's exchanges that happen in both directions, not just from the aquifer into the stream channel. So let's think about this question, one of the two questions I posed at the beginning of the lecture. What shapes a stream? Well, I've got a picture here of a stream channel that I've done a lot of work in over my career. It's Garvin Brook in southeastern Minnesota. And Garvin Brook, as you can see here, it's got kind of a U-shaped channel. No strong sense of scale in this picture, but I would guess right here the channel's maybe 10 feet wide. The water's maybe 4 or 5 feet wide. We've got very steep stream banks. There's a lot of vegetation here, so it's hard to tell. And if I were standing right here in sort of the deepest part of the stream, it might be a foot deep. And from the bottom of my feet to these stream banks is probably 5 to 7 feet. Right. So the question is, why is this channel this size? Why is it this width? Why is it this depth? Why is the actual water this depth? Why are the banks this steep? Those are questions we want to get at in this module. So to get us towards answering that question, we need to think about some of the processes that are going on in the stream channel and the adjacent floodplain. And so let's think about a stream reach here. So we're not thinking about the whole watershed, just a stream reach. And in the diagram here, we go from the upstream end to the downstream end. And let's talk about sources of sediment. So a big part of the sediment for this reach is probably going to come in from upstream. It will have been eroded from upstream sources, and it will be part of the input for this part of this reach. And we can also get inputs from tributary channels that come in from our side. But so those are external sources of sediment to the reach, but we also can have internal sources of sediment. We can erode the hillsides adjacent to the stream. We can erode the floodplain in the stream, maybe erode a bank here and cause that sediment to be transported downstream. And then some portion of this sediment that comes in or is derived from within the reach gets exported, and that's the lighter gray arrow here. So we have both inputs, the black arrows, and outputs are gray arrows. Now, we can also put sediment in storage within the reach. So some of the sediment that we erode, either sediment that comes in from above the reach or is derived from within the reach, may be stored in the floodplain as overbank deposition or new point bars on channels or new medial bars in the middle of channels. Right? Now, the other part of this to think about is we can think about this sediment budget just like a bank account. If we have a bank account and we make $1,000 a month, which would be the analogy to all our inputs here, our inputs from outside and inside the channel, but our expenses for the month, after we pay all our bills and have our fund money and all that stuff, our expenses are only $800 a month. Well, that leaves us with $200 left over. So that means every month we're accumulating more and more money in our bank account. Or conversely, and this is probably relevant to the average college student, if you have $1,000 coming in a month, but your expenses are $1,200 a month, that means you're going into debt every month. Now in the stream reach here, if we have excess sediment coming in relative to the amount that's being exported out of our reach, then we're going to have to store that extra sediment somewhere in the channel. That would be like a growing bank account. Our floodplain's probably going to have to grow vertically as we pile that sediment up higher and higher. Now, if our exports are higher than our imports, so our outputs are higher than our inputs, that means we're actually exporting everything that's coming in new, plus we're eroding some of what's already there in storage and exporting it out of the floodplain, and that means that the floodplain is going to have to be lowered because we're having a net loss of sediment, sort of like your bank account being drained month after month when your expenses exceed your income. All right, this is a cross-sectional view of a stream channel. In this case, it's the Colorado River at Lee's Ferry, Arizona. This is in the Grand Canyon. And unlike the streams that we're typically familiar with here in the Midwest, especially in southwestern Missouri, where I'm at, where Missouri State's at, our streams, our flow is driven by individual storm events. So we have base flow most of the year, but then we'll have a big thunderstorm come through, maybe dump several inches of rain in a short period of time, and we'll get a flood. Maybe we have a big snow dump in the middle of winter, and that snow melts rapidly when it's warmer a couple days later, and that causes some flooding. So we can have floods almost any time of the year, and they'll go up quickly and come back down quickly, and they're driven by these storms. But out west, especially larger rivers in the mountain west, their annual hydrology is driven much more by snowmelt. So the snowpack accumulates over the course of the winter, and say in mid-February here, February 14th, we've got sort of the maximum cold temperatures, the maximum snowpack accumulation up in the mountains, so all our water's tied up in snow and it's frozen somewhere in the watershed, and so we're really just seeing the minimal base flows that we're probably going to see for the year, and in this case it's about 135 cubic meters per second. Now fast forward a couple months to May 21st, And you can see that we've got a much bigger discharge. And because of this, the channel itself has grown. Now, think about the picture we showed of Garvin Brook earlier in this lecture. The water at base flow was only occupying just a small little bit of the channel. But during a flood, that channel will fill up progressively, maybe get to bank full, and then it'll even spill over into the floodplain. But that's kind of what's happening here is we've more than quadrupled the flow in the stream from February to May 21st. And as a result, we're filling up more of the existing channel. But also look down here at the bottom. Just as a reference height, the bottom of the channel here is just about in February at 0 meters. By May 21st, the channel has eroded down more than a meter on the left side here. And we've even eroded a little bit over here on the right side. If you look relative to where it's white background here, it's now blue channel over here. So we're both filling up the existing channel and we're eroding the bed lower to make more space. By June 3rd, which might be the peak of our flow, and that would correspond, it's taken all that snowpack that accumulated over the winter. Now we've got peak melting, so we're melting at the maximum rate. That's creating water in the system that's draining at the maximum rate, and we hit our peak discharge here in sort of the late spring or very early part of the summer. We've also eroded the bottom of our channel out quite a bit. Probably if we just look below that 0 reference line here, the stream channel, the new part of the stream channel that's been eroded out of its bed's bigger than the original base flow channel. We've filled the existing channel up even higher. So we've got a really big cross section. And then as we go through the rest of the summer, and more of the snow melt has completed, the discharges gradually come back down until by mid-August we're down almost to the base flow level that we had in February. And over that 6-month period, what's happened is we've depleted the whole snowpack. There's no more snow to melt, so we're just back down to base flow. But look at what happened to our channel here. Much of the sediment has been redeposited so that the overall size of our channel is about the same as it was in February, and the average depth of the bottom of the channel is right around that 0 mark, meaning that we had all this erosion through the summer that you can see here in May and June into our channel bed, but then we redeposit a lot of that sediment, new sediments that have come from upstream. We've redeposited, so there's no net change in our channel. And I'd just like to point out, even if there was just 1 centimeter of net erosion every year, if we eroded the base of our channel bed 1 centimeter per year, well, in 1,000 years that would be 1 meter. 1 meter is about 3 feet. In 1,000,000 years, that would be 1,000 meters or about 3,300 feet. So you could basically cut the Grand Canyon somewhere between 3,000 and 6,000 feet deep. You could cut the whole Grand Canyon in just 2 million years. 2 million years sounds like a lot of time, but geologically speaking, that's just a fraction of Earth history. It's a blink in the eye. So even a small net erosion rate can add up to a really big trench in the ground, the Grand Canyon, in a relatively short period of time. Right? So if we have a stream in equilibrium, what we're going to see is over a longer term period, years or decades or centuries, there'll be no net change in the elevation of the stream or the floodplain. We'll have equality between our inputs to the channel in terms of sediment and our outputs to the channel in terms of sediment. All right, this is a good stopping place for the first half of the Streams Job lecture. I'll continue this lecture in part 2 just to keep the 2 videos a little shorter. So we'll see you in just a few seconds, hopefully, on the second part.